Hello friends, welcome to my second lecture on Cauchy type integral equations. We will begin with Cauchy type integral equation on the real line, the equations that are of the first kind. In the first kind we shall consider the singular integral equation, integral 0 to 1. This is star means we are considering the principal value of the integral. So integral 0 to 1 gt dt upon t minus s. You can see that because of t minus s in the denominator and s lying in the open interval 0 to 1, the integrand becomes unbounded over the interval of integration 0 1. So integral 0 to 1 gt dt upon t minus s equal to fs, where the integral is understood in the principal value. So this is Cauchy principal value. A star denotes the Cauchy principal value. Now the kernel here is ks minus t upon 1 minus t 1 upon t minus s. This kernel is said to be Cauchy kernel, and the equations involving such type of kernel are called as Cauchy type singular integral equations. Now here we have taken the limits of integration to be 0 1, but they could be any real numbers a and b. By suitable substitution we can make the limits of integration to 0 1. So the limits of integration in equation 1 can be taken to be any real numbers a and b instead of 0 and 1, because by a simple translation and scale expansion we can reduce the integral over a to b to the case integral over 0 1. Now let us first consider the special case where the limits of integration are 0 and 1. So to solve the equation 1, we proceed as follows. The integral 0 to 1 gt dt upon t minus s. gt dt upon t minus s equal to fs. We can write it as let us multiply both sides of this equation by s. So when you multiply by s, since the integration is with respect to t, so I can take s inside and this will become then fs into s. So now I can write it as integral 0 to 1, instead of s I can write s minus t plus t times gt dt divided by t minus s equal to sfs. Or I can say this is minus integral 0 to 1 gt dt, s minus t will cancel with t minus n and we will have a minus 1 here, plus integral 0 to 1 t times gt dt divided by t minus s, which is equal to sfs. Or we can say integral 0 to 1 t times gt dt divided by t minus s. This is equal to sfs plus integral 0 to 1 gt dt. Let us denote, because integral 0 to 1 dt will be a constant, so let us denote it by c. So denoting integral 0 to 1 gt dt by c, we get integral 0 to 1 t gt dt upon t minus s equal to sfs plus c. Now for convenience we are not writing here star, but it is always assumed that we are considering the principal value of the Cauchy integral. So for convenience we can simply write integral 0 to 1 without a star, but it will always mean that we are considering the Cauchy principal value. Now Now multiplying both sides of this equation, let us multiply both sides of this equation by ds over square root s into u minus s and integrate with respect to s from 0 to u. So we shall have integral 0 to u 1 over square root s into u minus s, integral 0 to 1 t gt dt upon t minus s ds, and then we have integral 0 to u root s into fs upon square root u minus s ds, because this square root s will cancel with s here and we will get square root s left. So square root s fs upon square root u minus s ds plus c times integral 0 to u ds upon square root s into u minus s. Now s and t are varying independently here, so we can change the order of integration and write this also as minus integral 0 to t t gt dt, then 0 to u 1 over ds over this t minus s we are writing as s minus t and put a negative sign here. So s minus t is square root s into u minus s, and this is same as here integral 0 to u root s fs ds upon square root u minus s. The value of this integral is equal to pi. Let us see how it is pi. So integral 0 to u ds upon square root s into u minus s. We can write it also as integral 0 to u ds upon s into u 1 minus s by u. Now let us put s by u equal to t, so that ds is equal to u dt. Then this will be equal to when u is when s is 0, t is 0, and when s is equal to u, t is equal to 1, ds is equal to u dt. And what we will have in the denominator, s is equal to u into t, so u square into t 1 minus t. So this will be nothing but integral 0 to 1, this u square, square root of u square is u, so it will cancel with this and we will get dt upon t times 1 minus t square root, which is equal to integral 0 to 1 t to the power minus half 1 minus t raised to the power minus half dt, or we can evaluate it by beta function 0 to 1 t to the power half minus 1 minus t raised to the power half minus 1 dt. So we shall have gamma half divided by gamma half plus half, and this is gamma 1 is equal to 1, gamma half is equal to square root pi, so square root pi whole square, so this pi. So we get c into pi here. So this expression comes after we change the order of integration here and put the value of this integral by using beta function. Now let us make use of this identity which we have proved earlier. When you use this identity, how we get the expression, the quotient 2. So let us go back to the equation, this one, but we have minus integral 0 to 1 t gt dt, or inside we have integral 0 to u ds upon s minus t square root s into u minus s. This is equal to 0 to u square root s into fs divided by square root u minus s plus c pi. Now we go to the identity which we proved. So integral 0 to u ds upon now what we'll do here, yes, the integral is the outer integral is with respect to t, where t varies from 0 to 1. We can break this into two parts, 0 to u and u to 1. So this can be written as r minus integral 0 to t t gt dt integral 0 to u ds over s minus t square root s into u minus s plus integral t to 1 0 to u, not 0 to t, 0 to u and here u to 1 t gt dt integral 0 to u ds over s minus t square root s into u minus s equal to right side 0 to u square root s fs divided by square root u minus s plus c pi. Now when we use this identity, then this part integral 0 to u, here t varies from 0 to u, so this expression becomes 0 and therefore this part vanishes, and here we will put the integral 0 to u ds upon s minus t s root s into u minus s from here, because t varies from u to 1. So this will be reduced to when you put the value, this will become r integral u to 1 t gt dt minus integral 0, so this will become pi upon root t into t minus u equal to 0 to u root s fs ds divided by square root u minus s plus c pi, and we can write it as okay. We can further simplify this. Root t will get cancelled here and we will get root t here. So integral u to 1 root t gt dt upon root t minus u equal to, we can divide by pi. So 1 upon pi integral 0 to u root s fs ds by root u minus s and then c. So this is how we get this equation, and this equation is nothing but, this equation is called as the Abel's integral equation. So now let us see how we solve this further. So let us recall the solution of the Abel's integral equation. We have earlier studied Abel's integral equation of this type. Fs equal to integral s to b gt dt upon ht minus hs to the power alpha, where 0 less than alpha less than 1 and a is less than s less than b, and ht is a monotonically increasing function. We have seen that its solution is gt equal to minus sin alpha pi over pi d over dt integral t to b h dash u fu over hu minus ht to the power 1 minus alpha du. So we will make use of this article to proceed further. Now let us see what we have. This is our equation, integral u to 1 root t gt dt divided by square root t minus u. This is equal to c plus 1 over pi integral 0 to u root s fs ds divided by square root u minus s. and we will be using this result. So let's see how we make use of this result. So okay, so let's see, let us apply this result to this one. This is square root u to 1. So this side, integral u to 1 root t gt dt upon square root t minus u. When we solve using this equation, what we will get? We have fs equal to integral s to b gt upon gt dt. This is the integral equation, ht minus hs to the power alpha, 0 less than alpha less than 1. When we have this equation, then we get gt as okay, then gt is equal to alright, minus sin alpha pi divided by pi d over dt of integral t to b h dash u f u du over h u minus h t to the power one minus alpha. Okay, let us see how we make use of this. So here we will make use of this integral equation is similar. This integral equation is similar to this one. Instead of s here we have u, instead of 1 here we have b, here we have 1, and this is our known function fs. This is known thing, so this is fs, this is fs, and this is known to us, which is after integration gives you u. So actually what is happening here is that the known function after integration gives you a function of u, while here we are writing it as a function of s. So instead of s here we have u here, and here what is happening when we integrate, and gt is the unknown function that we have to find. So when you apply this, what we will get? Okay, so when we make use of this solution of this Abel's integral equation, then we will get integral square root s gs equal to minus 1 over pi d over ds integral s to 1 c over under root u minus s du minus 1 over pi square d over ds integral s to 1 over square root u minus s 0 to u square root t f t dt over square root u minus t du. Or we can say that this is integral square root u s into gs c upon under root 1 minus s minus 1 by pi square d over ds integral s to 1 du upon square root u minus s 0 to u root t f t dt over root u minus s. So this you can get how we come here, c upon root pi root 1 minus s, you can integrate s to 1 du upon square root u minus s. When we integrate, and this is what, s to 1 u minus s to the power minus half du. So this gives you after integration u minus s raised to the power half divided by half, so that is 2 times this, and then we get here, let us put limits. So what we get, 2 times 1 minus s to the power half. Now we can differentiate it with respect to s. So d over ds of integral s to 1 du upon u minus s square root is equal to 2 times d over ds of 1 minus s to the power half. So this gives you 2 times 1 over 2 1 minus s to the power minus half. So we get, this is how we come here, c upon pi under root 1 minus s. Now let us change the order of integration here. So let us change the order of integration here and see what happens. Okay, so let us now change the order of integration. We have here the limits of integration like this. T varies from 0 to u, t varies from 0 to u, and u varies from s to 1. So if we draw the figure to change the order of integration, then this is my t axis, this is u axis, this is the line t equal to u. Now t varies from 0, so t is 0 on the horizontal axis, t varies from 0 to u, and u varies from s to 1. So let us say this is u equal to s line and this is u equal to 1. So this is the region over which we are integrating. In this limits of integration we are taking a vertical strip, because when you take a vertical strip, then for the vertical strip t varies from 0 to u and u varies from s to 1. Now when we want to convert, when we want to change the order of integration, we will have to divide this region into two parts and take the horizontal strips. So in this part, when we take the horizontal strip, then for the horizontal strip you can see that u varies from s to 1 and t varies from 0 to t equal to s. And when we take in the upper part, in this part, then in this part u varies from t and u goes up to 1, and t varies from s and t goes up to 1. So this is how we change the order of integration. And then we have 3 upon pi square root 1 minus s minus 1 upon pi square d over ds. Now here integral s to 1 and t is less than s, because 0 less than t varies from 0 to s. Here t is more than s, because t varies from s to 1. We can combine these two integrals and write integral 0 to 1 square root t ft dt maximum over st maximum st 1 du upon square root u minus s into u minus t, because when you can break the 0 to 1 into two parts, 0 to s and s to 1, and then this expression will give you this one and this one. On changing the order of integration, and we can combine these two integrals in this form. And then now let us use the identity which we had proved earlier, maximum st to 1 du upon square root u minus s u minus t equal to this. We find that gs comes out to be c upon pi root s into 1 minus s 1 by pi square into square root s into 1 minus s integral 0 to 1 square root t 1 minus t ft dt over s minus t. Now we will have to differentiate this expression with respect to s because of d over ds. That we can do by considering two cases when t is greater than s and s greater than t. So by taking two different cases, we can differentiate this expression with respect to s, and we will get this quantity. So now what we do is we put t equal to t dash minus a over b minus a, s equal to s dash minus a over b minus a to change this interval of integration from 0 1 to a b, and then we get the solution to this equation, the principal value of integral 0 to 1 gt dt upon t minus s f t a less than s less than b to b gs equal to this expression. So this is the solution of the Cauchy integral equation of first kind. For example, suppose we have this equation integral a to b gt dt upon t minus s equal to 1 a less than s less than b. Then here the function fs is given to be equal to 1. So making use of that, we can put it as gs equal to c upon pi square root s minus a b minus s. A is equal to 0, b equal to 1 we are given. So c upon pi square under root s into 1 minus s 0 to 1 square root t into 1 minus t, and ft is given to be equal to 1. So we have this dt integral interval of integration is AB, okay, sorry, interval of integration is AB, so we will get this. You can simply put ft as 1 here, and we get the solution of the this Cauchy integral equation of first kind. With that, I would like to conclude my lecture. Thank you very much for your attention.